So today we're going to classify some things with our graphing. The first thing we're going to look at are stationary points. Now, stationary points are any point where the tangent is 0. It includes maximums and minimums, and we're also going to learn that it includes some other points called stationary points of inflection. So anytime that you have a curve, there's a fun curve. Anytime you have a curve where the tangent is equal to 0, you'll have a stationary point. So if you drew a tangent at a point at a maximum or a minimum, or if the curve flattens out in the middle like an x cubed curve does, then the derivative is going to equal 0, and that's called a stationary point. So the three types of stationary points are those maximums, minimums. They make sense, and that one that I drew in between is called a stationary point of inflection. Now, for maximums and minimums, what happens at that stationary point is your derivative changes. Does it make sense that any point on this side of your maximum has a positive slope, and any point after that maximum has a negative slope? So if your slopes change from positive to negative, you'll have a maximum. And if they change from negative back to positive, you'll have a minimum. You have what we call relative maximums or relative minimums and absolute or global extrema. What that's saying is sometimes in a graph, like this first one that I drew, this one is a relative or local maximum. It's a maximum. If you visit all of its friends and it's nearby, like if we draw a circle around that and say this is a little town and these are all the people living in the town, this is the guy that has the most money, or I don't know, is the tallest, okay? And he feels all big in his little town because he has the most money, or he's the tallest in his town. But if you look at this graph somewhere later on, because this graph keeps going up, there are people that have more money or are taller than him, but in his little local town, in his little area, he's the biggest. Same thing with the minimum, right? This is the guy in his town that's the shortest, or has the least amount of money. But the graph somewhere else might have further on. So we call these ones that are in a smaller area a relative extrema, or a local min or a local max. And then if you're finding the one that's the biggest in the whole graph, that would be the absolute maximum. An inflection point, by definition, is where a graph changes its curvature. So we call this part here, because its curve is kind of like a sad face, we call that concave down. And this part over here, where the curve is up, we call that concave up. So if something changes from concave down to concave up, that's an inflection point. Oh, this one was relative, and that's absolute. And if there's a point in between, a place where it changes its concavity, it changes from concave down to concave up, where the slope is 0. So according to this picture here, if I drew a tangent at that red point, it would have a slope of 0. This is called a stationary point, because its slope is 0, of inflection. It's not a maximum, it's not a minimum, but we still have a stationary point there. So the first derivative test is a test to find out if something is a maximum or a minimum, a local max or a local min. You have to first of all find out that you have a critical number at that point. Usually you find out that that's a critical number because the derivative is equal to 0. Remember, critical numbers were either the derivative was equal to 0 or non-permissible values. And then once you have a critical number, you will be able to tell that it is a relative maximum or local maximum if the derivative changes from positive to negative. Now, we already showed this when we were doing our graphing the other day. The other day, remember how I connected the idea of drawing that sign diagram? And so you found some critical number, I'm going to call it C. And if we found out that our derivative was positive before, that meant our graph was increasing. And then negative afterwards meant that it's decreasing. You can tell that this point has to be a max. That's the only way it makes sense. Because our derivative is equal to 0, and that point has to be a maximum. Secondly, you could have a relative minimum or local minimum if the other thing happened. You have your critical point here. It's negative, meaning that your graph is going down, followed by going up. That tells us this has to be a minimum. So for our first derivative test, we need to show two things for something to be a maximum or a minimum. First, we need to show that the derivative is equal to 0. In other words, we have a tangent that's flat. Then you have to show that it's increasing before and decreasing after for a maximum, or decreasing before and increasing after for a minimum. Go back. There you go. So here's a parabola. It says find the stationary point and then show that it is a maximum using our first derivative test. So for our first derivative test, we need to show that find that critical point by making the derivative equal to 0, and then use that sign diagram to show where it's increasing and decreasing. And if we can show that it's increasing before and decreasing after, we'll know that it's a maximum. Okay? So our derivative is going to be negative 2x plus 5. Setting that equal to 0, we get that x is equal to 5 over 2. This is our critical point. When we draw our number line, that is the only critical point since we have no non-permissible values. It's 5 over 2. If you plug in something before 5 over 2, and remember, when checking whether a graph is increasing or decreasing, you're plugging that into your derivative, because that's what your derivative is saying. If you're plugging something into your original function, Carter, your phone. If you plug something back into your original equation, all that's going to tell you is a point on your graph. So if I plug in 0, I'm going to get a positive value here, meaning that it's increasing. And if I plug in something bigger than 5 over 2, like 10, and if I plug that into my derivative, I'm going to get a negative 15, which means I'm going to have negative slopes here, meaning that our graph is going down. So how can we write this using the first, if we wanted to write a statement to show that we know this with the first derivative test, we could say, we know that 5 over 2 comma, I'm just going to plug that into my equation to find out what that is. That's the point. So I plugged in 5 over 2 for x into my original equation and got negative 3 over 4. We know that this is a max or maximum because f prime of 5 over 2 equals 0. So that's the first thing, to show that the slope is equal to 0. And f prime of x is greater than 0 before x equals 5 over 2 and f prime of x is less than 0 after x equals 5 over 2. Okay? If we add words, what does this mean? It means that that f of x is increasing before x equals 5 over 2 and decreasing after x equals 5 over 2. That's the first derivative test. There will be questions that ask you to explain that something is a maximum using the first derivative test. And later we're going to learn the second derivative test to show that something is a maximum or a minimum. So I'm just trying to be really clear right now that there's going to be two of them, and you're going to need to know the difference between the two of them. But for the first derivative test, it's exactly this sign diagram. It's saying that the derivative is equal to 0, and that increasing then decreasing makes a maximum. Okay, here's one for you to try. Any questions so far? Again, it's not, yeah, go ahead. So when I say that f prime of x is less than 0 before, that's showing this negative right here. Because we figure out when we plug in a value less than 2, and we find out it's negative, that means this whole section is going to be negative, which means that our original function has to be decreasing before. And the same thing with the positive. That's what it means for before and after. And when we say after or we say before, in this case it doesn't matter because anything after 2 is going to be positive, anything before 2 is going to be negative. But you're going to have some questions that have more than one critical point. So when we say before, we're meaning like immediately before. Like just before it, it's negative. Because if I had another point here and the graph went up before that, if I chose something before 2 too far, I would get a different kind of result. So when we're talking about something before, we are talking about just before it. But in this case, it doesn't matter so much because there's only the one critical value. You know how to find max and mins on your calculator. If you wanted to find the actual point, you could graph it, use the second trace button, and find points that way. Oops. I want to go back to this one so I can enjoy pushing this button. There we go, inflection. Stationary points of inflection. So what's going to happen in order for us to find out that it's an inflection point? We're going to be doing that same idea, drawing our number line, putting our critical point on there. But then when we check things, it might be that this happens. It's increasing before and increasing after. Well, that would be very similar to what happens with an x cubed graph. Can you see your graph is increasing? And then there's a critical point right there where the tangent's 0, and then it increases afterwards. So if your graph is increasing on both sides or decreasing on both sides, in other words, if the gradient or the slopes of your tangents are either both positive or both negative, then you know you have this stationary point of inflection. And any time that you have a stationary point of inflection, you're going to find out that the second derivative at that point is also equal to 0. So what I mean is, I've told you there's 1 with x cubed. If I take my first derivative, I get 3x squared. If I set that equal to 0, you get x equals 0. So on there's your critical point. You plug in a number before 0 into your derivative, it's positive going up. Plug in a number afterwards, it's positive going up. If you do your second derivative, you'll get 6x. If you set that equal to 0, you get the same value. And that's what this statement here. If there's a stationary point of inflection, the value of your second derivative will also be equal to 0. And we're going to find that out later, that we're not only going to find stationary points of inflection, we're going to find other points of inflection as well. And inflection points always happen when your second derivative is equal to 0. Yes? Yeah. X cubed, yeah. Well, you could have negative x cubed, right? That would be a graph that's... Yeah. Yes, you have some x cubed graphs that go like this, right? Yes. Those x cubed graphs have other information, depending, like this one might be x times x minus 3 times x plus 2. Okay, then I have an x-intercept at minus 2, an x-intercept at 0, and an x-intercept at 3. Then this would happen. As far as critical points go, this one you would have a critical point here and a critical point there. And on those number lines, I'm going to call this one C1 and C2, you'd have both of those, and you would go up, then down, then up again. And none of those would be stationary points of inflection, because this would be a max, C1 would be a max, and C2 would be a minimum. And later on, we're going to find out that here, call that point I for inflection point. Can you see that that's where this graph changes from being concave down to concave up? So we're going to find that point as well later on for our curve sketching. But the ones that we're looking at right now are where those things happen at the same time. You get a critical point, but it's not a maximum or a minimum. And that the basic x cubed graph is one graph that does that. Here is an x cubed graph that isn't just a basic x cubed graph. It has some extra stuff involved. So if we were going to find all of our stationary points and classify them, we'd start by finding our derivative. We'd set our derivative equal to 0. I'm going to factor out a 3x. And then we find out that x could be 0 or x could be negative 2. This one has 2 critical points. If I draw my number line, negative 2 and 0 on there, again, this is where we're going to use our factored form of our equation to help us figure things out easier. For example, I'm going to choose something in this first section less than negative 2. Like negative 5. I'm not going to do the mental math exactly. I can, if I want to, I could. But plugging in a negative 5, 3 times negative 5 is going to be negative. And negative 5 plus 2 is going to be negative. And so I have a negative number multiplied here by another negative number that is going to be a positive number. I know my graph is increasing in this section. Plugging in a number between -2 and 0, like -1. This first number is still negative, but now -1 plus 2 is positive. A negative times a positive is negative. I know in this section my graph is decreasing. And finally, something larger than 0. That'll make both of those sections positive. Positive times a positive is positive. It's increasing. So what do we know? We know that at -2 comma, if I plug in -2, I'm going to get -8 plus 12 plus 1 is 5 is a local max. I can see that by my diagram. And 0, 1 is a local minimum. I can also see that from my diagram. All right, one for you to try.